So in my last class, I discussed about few properties of graphs, mostly the connectedness, the component definition of component, and few relation among the number of vertices, number of edges, and the number of components that may exist in a graph. Today, we are going to actually start with a puzzle maybe. So let us consider the Olympic rings. So we know that in Olympic ring we had five such rings and they are interconnected, right? So we consider five such rings, this and say this. Okay. Now, suppose here we consider, since we are considering graph theory, so we consider here as maybe this as the vertices and the remainings are edges. So here, how many vertices will be there? If we consider this junction as vertices, then we will have basically say this is V1, this is V2, this is V3, say V3, V4, V5, V6, V7, and V8. And the remaining are edges. So how many edges are there? Say E1, E2, E3, then E4, E5, E6, E7, E8, E9, E10, E11, E12, E13, E14, E15. Is there any age that I missed? Maybe here. Okay. So it's E16. Any age I missed? I guess I explore all the ages, right? So here, yes, all the edges are there. Okay. So now you can see that there are 16 edges and 8 vertices. Okay. Now we are going to play a game. So I hope that all of you must have some pen and pencil with you. So try to draw a path. So I hope you all know what do you mean by path and walk or trail. Last day we talked about this trail, path, and walk. So now we are considering first a walk. That means you should start from a vertex, and I want some closed walk. That means a circuit. Starting from some vertex, say V1 will be my starting vertex, and V1 will be my end vertex. Okay. Now start with this vertex, explore all the edges exactly once, and the idea is you cannot, if you start pointing your pencil or pen here, you cannot uplift your pen, okay, from here. That means starting from here you have to explore all the edges exactly once, and you should come back to V1 once again. I am again repeating. The idea is you cannot lift your pencil from the paper. Once you have, suppose you have touched the pencil at V1, then you should come back to V1 once again by exploring all the edges of the graph exactly once. Then only you will able to lift your pencil. First of all, the first question is it really possible to do so? If so, give me some path. If give me some walk or circuit. If not, then tell me why it is not possible. Is the question clear to all of you? So I want a walk, that means kind of alternating sequence of vertices and edges in which the vertex may repeat, but you cannot repeat the edges, and you have to explore, or you have to go through all the edges exactly once. That means if you go through this, then that is exhausted, you cannot go back to like this. Okay. Now try to solve this problem. and give me some solution, or tell me that this is not possible. If you can find such edge or some closed walk or some circuit, as I mentioned in my earlier classes, or trail, then give me that. So give me a trail or give me a walk, closed walk, exploring all the edges exactly once, and you start from V1 and you should come back at V1 once again. Okay, let's see. Is the question clear to all of you?
Yes, sir.
Okay, so please try and let me know. In the meantime, I will draw some extra. So please keep the nomenclature or keep the name of the edges and vertices same. Otherwise, your answer may be, while you will explain me, your answer may be different. Okay, then it would be difficult for remaining people to understand what is your path or what is your trail or what is your circuit, etc.
Yeah, then if we start from V1, then it won't be possible because in the diagram, if we start with either of E1 or E3 edge or
Yes,
E2, either one of E1, E2 or E3, then
yes,
we move to V2 if we choose any of them,
yes,
and then we choose one of if we choose one of the remaining two of them, then we get back to V1.
yes,
Now, if from that place from V1, then if we choose the last of E1, E2, and E3, then from V2 we have to move. We have to take the edge E5, and then the edge E4 won't be taken in any possibility, because whenever we take E4, then we don't have a path to get back to V3 from V1.
yes, but it's not mandatory that you should always come back to V1 from within this first
Yeah, yeah.
two
Then the second
numbers.
case, if we don't take I mean, if we don't move to the last part, if we just take two points out of I mean two edges out of three, E1, E2, or E3, then we are remaining at V1 and we have one edge left to be used. Then from V1 we have to take E4 to V3, and then we have to have only one path for coming back to V2 is E5, and then from using E5 we go to V2, and then again from V2 to V1, and then we are stuck again. And if we don't use these two things, only use one edge, then the first problem will repeat. So in either of the cases, we are not being able to complete the whole thing.
Okay, it's a good try. Let's see what's about others. Okay, shall I show you one path or you will? I mean, trail or you will? Anybody? Okay, I'm sure if you are given with sufficient amount of time, you will suddenly find such. Let us try to see. Okay, so I'm starting from here. I will go here, then move like this, this. Then I will this, then then this. Come here, come back here, and come back here. Can you see this? I guess now I have explored all the vertices and all the edges. The main aim is to exhaust all the edges exactly once, and I need to come back to the original position. So is the path clear? And this is not, of course, an unique path. You will certainly find many more such, not path, many more such circuits or trail in this particular graph. So is the solution clear to all of you? Is it clear?
Yes, sir.
Yes, sir.
Okay. Now, can you tell me the similar problem? Like I will start from here. I will travel all the paths exactly once, and I want to come back to A once back. Okay. The idea is start from here. Say I will take this path. I'll come here. I'll come here. I'll come here. I'll come maybe here, and then I come here. But see, if I do that, two of the edges are not explored. So this won't be a solution. So I need to solve this. And that was actually the famous problem of Konigsberg bridge problem. And it was around 1736 or 7, something like that. So during that time, it was the famous problem, and I started taking my classes with explaining this problem itself. So that's known as Konigsberg bridge problem, and Euler for the first time solved this by using the graph theoretic technique, and that's why it's considered to be the first paper on graph theory, and Euler is considered to be the father of graph theory. So in my first class, we have already concluded that if your graph is like this, you cannot go back from A to A, exploring all the edges exactly once, because the degree of these vertices, if we have the degree of this vertex is 3, the degree of this vertex is 5, the degree of this vertex is 3, and this is also 3. So this, since the degrees are odd, it's not possible. But if you look at here in this graph, the degree of each vertex is even. See, either this is 1 2 3 4, this is 1 2 3 4, 1 2 3 4, 1 2 3 4, and so on. So degree of each vertex is even. So the natural question comes to our mind is, if the degree of each vertex in a connected graph is there, and that is even, then do we really have this problem, or can we really trace the whole paths or whole edges exactly once? And the answer was yes, and it was done by Euler, and it's known as Euler's characterization. So when a graph uh, is having this property, so now you can understand that in a graph, what we are interested here is that in a connected graph, we are trying to find a trail, that means a walk, in which no edge will be repeated more than once, and from where we start, we should come back to the same point, exploring all the edges exactly once. So that was the same problem as Konigsberg bridge problem, and it was shown that it is an if and only if condition. That means a connected graph is said to be Eulerian if if the degree of each vertex is even. So it has to be first a connected graph, and if the degree of each vertex is even, then certainly we will trace this kind of graph. That means we can start from a particular vertex, any vertex, then we can come back to that vertex by exploring all the edges of the graph exactly once. And it will happen only if, and if and only if the degree of each vertex is of even degree, and of course the graph must be connected. So if the graph is connected and the degree of each vertex is even, then suddenly you will able to trace that graph satisfying that property. And conversely, if you can uh, trace all the vertices exactly once, uh, then the graph, that graph has to be connected, and then the degree of each vertex will be given. So that's a very interesting problem, and you can see that in this graph you have the degree of each of these vertices is even. As a result, you can certainly have this kind of uh, path or this kind of tracing property, and that is known as Euler's, uh, you can say this Euler's walk or Euler's line. Okay, so I'll just following as I mentioned, it's by the Norsing Deo's book, and it's section 2.6, this Euler graphs. So it was saying that in mentioned in chapter 1 in my previous first class, I also described the same problem. This is 1936 with Euler's famous paper in which he solved the Konigsberg bridge problem. In the same paper, Euler posed a more general problem. In what type of graph G is it possible to find a closed work running through every edge of G exactly once? Such a work is now called an Eulerian line. So somebody says Eulerian line, some author it said Eulerian circuit. And the graph that consists of an Eulerian line is called an Eulerian graph. More formally, if some closed work in a graph, then the work is called an Eulerian line and the graph is called an Eulerian graph. So you can understand this our Olympic because it contains at least one Eulerian line or Eulerian circuit. Okay. By its very definition, a walk is always connected since the Euler line, which is a walk, contains all the edges of the graph. An Eulerian Euler graph is always connected, except for any isolated vertex the graph may have. So if a graph has only one vertex, we then call it as connected, and that is, say V is then in a special form we call V as the Eulerian walk or Eulerian line. Since an isolated vertex do not contribute anything to the underline of an Eulerian graph, it is thereafter assumed that Eulerian graph do not have any isolated vertices and are therefore connected. So we consider all the graphs here to be connected for Eulerian graph. So it says that now we are going to state the theorem that I have just mentioned to you. A given connected graph G is an Eulerian graph if and only if all vertices of G are of even degree. So just now I have mentioned and I have shown you the graph as I mentioned there. So I'll just leave this proof of the statement to you. So it would be your reading course. Maybe someday I will ask you to prove it. So just try to understand it. It's not very difficult. It's quite easy to understand. Now, if I ask you the question, can you modify? I have already asked you the question. Now it will be quite clear to you and quite easy for you to give me the answer that in this bridge, can you add few extra bridge so that uh, it will have this problem, like it will start from A and it will be able to come back to A exploring all the bridges. So you understand that at the initial stage when the Konigsberg bridge problem was stated, at that time you cannot have this property of Eulerian graph. But now I am telling you, just try to introduce few more bridges on it so that your new problem becomes I mean in the new graph will be able to, in the new graph you will able to find an Eulerian circuit. Can anybody be suggest some of the new bridges so that we can have the corresponding graph becomes an Eulerian graph? Any new age that you can suggest? Anybody? Which bridge that you should, or in terms of graph, what would be your m, so that that becomes an Eulerian graph. Okay, maybe Kolpok, are you here?
Yes, sir.
Yes, can you tell me? So from A, the degree is 3, and this degree is also 3. So one edge may be this, and this degrees you need to increase, and if you have like this. So now the degree of C becomes 1, 2, 3, 4, 5, and 6. So even number. The degree of A becomes 1, 2, 3, and 4. The degree of B becomes 1, 2, 3, and 4. And the degree of D becomes 1, 2, 3, and 4. So now all the degrees of these vertices are even. As a result, this is now an Eulerian graph. And the problem that was actually posed in terms of Konigsberg bridge problem was solved. And I read in the internet that now these two extra bridges has been introduced in that river, on that river, to solve this problem. So now the problem is being solved here. So it's so now you can understand that this graph theory nowadays
Sir,
are
we can
very
show
much.
that sir,
Sorry.
actually, I was asking that how we can show that it is not possible with one bridge or one extra edge.
No, that if you have, then you have to, because here there's a finite number of vertices, so you can explore that. That would be one way. If you add all possibilities between any two vertices, you just try to incorporate one extra edge, then you will find that there will be some vertex which will not be of even degree. Okay, then you will your graph will not be an Eulerian graph. But it has been found that you need to incorporate two of the vertices, two of the extra edges, that will make the whole graph uh, Eulerian. So that's why two edges were required. So you can check that. So there are only four vertices. So take all the six possibilities. So some extra edge that you may try to incorporate, and then you find that okay, still some few things are left. So as a result, you need to check. It's not possible. Then you have to introduce extra more edge to get the answer. Okay. Okay. So let us now come to that problem. This is Eulerian things, and there are few such Eulerian graphs are also here. So you can try with this. You can give a naming of that, and then try to find whether that is Eulerian. So you can see that they all of them are Eulerian because the degree of each vertices are even, either 2 or 4. So that is Eulerian. So can you just try to find some of the uh, trails or some of the works, so that it will contain, you can be able to show you some of the Eulerian circuit and all. So that could be quite an interesting problem. But here some few more terms are there. So in case of Eulerian graph, you had that property that it should start from a particular vertex and it should end at that particular vertex, exploring all the edges exactly once. Now, in some cases, for some practical purposes, it might happen that it may not have that property, that it should also come to the come back to the original vertex from where you started. That means it may be the case that suppose you started from the vertex A and you end up with B, but exploring all the edges exactly once. That means it may not be a closed work. So there are few names on that, and one of this formal, we call this kind of lines as unicursal graph or unicursal line, and the graph having this unicursal line We call it unicursal. Say, you can see that the degree of not all the vertices are even. Okay, so here this is odd degree vertex. Here also we have odd degree vertex. So suddenly it is not an Eulerian graph. Now, if I ask you in this form that okay, it's not Eulerian, but can you find some of the work in this graph so that it starts from one vertex and it may end to some other vertex, say B, but it explores all the edges exactly once. That means you may not have to start from A and you should come back to A. As you can understand, this is a connected graph and not the degree of each vertex is even. As a result, you cannot have this graph with you. So it cannot be an Eulerian graph. But can you have this property that it should start from some vertex and it may end at some other vertex, exploring all the edges exactly once? So that's the idea. Can you tell me any of this path so that I start with say A?
Yes, sir.
That
Sir, we go from A, we go to C.
okay. So from A go to C. Okay. So just in an one, then C, then
Then we go to C to D.
okay,
Then we
then
come back to A.
come back to A through S.
Then we go to B using 4.
Uh, 4.
Then we come to D using 5. Then we go
Okay.
to E using 6. And then we go to B again using 7.
So let us try to check. One edge is there, two is there, three is there, four is there, five is there, six is there, seven is there. So we explored all the seven edges and we start with A and it comes back to B without repeating any of this edge once again. So it is the only exactly once we explored all the edges exactly once, but we explored all the edges. So for some practical purposes, this kind of graphs are also very important, which explores all the edges exactly once, but it had the it's not Eulerian because is not starting from A and it ends up at A, because you cannot have, because we have already the theorem at our hand that to achieve that kind of property, the graph should have this particular property that every vertex should be of even degree. But here we can see that at edge the degree of A is exactly 3, so it's not really possible. But in that graph we can certainly explore all the edges exactly once, but it should not start with some vertex and end with that particular vertex. So that kind of graph is known as unicursal graph, and that this you can say this work is known as unicursal line. Okay, so it's here. Is it clear to all of you the concept of unicursal graph?
Yes, sir.
Okay, so let us now let us now try to have this theorem. This theorem says that in a connected graph G with exactly 2k odd vertices, there exist k edge disjoint subgraphs such that they together contain all edges of G and that each is a unicursal graph. So what is the meaning of unicursal graph? I have just explained. So in the Eulerian graph, there will be a closed work. That means that should start from a vertex and that should end up to the same vertex, exploring all the edges exactly once. Now in some graphs, it may happen that you may start with some vertex and you end up with some other vertex, but you can explore all the edges exactly once. For example, here this is the example of the graph where you can, so just now I have written, so this is a kind of work which starts with A and ends with B, and it explores all the 7 edges of the graph. So here you can understand that you cannot come back to A having all these properties, exploring all the edges exactly once, because it's not an Eulerian graph, but it's a unicursal graph in the sense that you can have a work through which you can explore all the vertices, all the edges exactly once. Okay, now this theorem tells you about some properties of unicursal graph. So for example, suppose we consider some extension of it. Maybe I just have some extra. Okay, maybe I can put it here, some extra. So till how many vertices were there? A, B, C, D, E. Okay, up to E. So it was F, G, H, say I, and say age were up to 7. Then this is 8, 9, 10, 11. So now this is my graph. Now you can understand that. So 1, 2, 3, 4, 5. 1, 2, 3, 4. Okay. So now you can understand that this is certainly not an Eulerian graph, because this degree is odd degree. So at least one odd degree vertex means it cannot be a Eulerian graph. But can we have a unicursal graph here? Can you find, okay, the first question is this graph, now it was not the original graph. So now my question is, okay, I can just remove it from here. So now my question is, this is now my graph having uh, vertices up to G, okay, G, not G, it's up to I, and with maybe 10, 11 edges. Now my question is this graph an unicursal graph, a unicursal graph? Can you find a path from somewhere? Can you find some starting from say A? Can you go back to some particular vertex which is not A, exploring all the edges exactly once? Is it really possible?
No, sir.
It's not really possible, because you can understand that once you go at some end, then there will be no chance to come back here again, right? Then you will have to explore uh, such extra edges twice. Now come to this theorem, that then statement will be clear. So it says that in a connected graph with exactly 2k odd vertices, let me see how many odd vertices are there. This is odd degree vertices, so the degree is here 3. This is even 1, 2, 3, 4. This is even 1, 2, 3, 4, 5. So this is odd degree vertex, and this is, so this is odd degree vertex. This is odd degree vertex. This is odd degree. This is odd degree. So how many? 1, 2, 3, 4, 5, 6. Okay. So there are 6 odd degree vertices are there. That means 3 into, so 2 into 3, 6. So is a connected graph with exactly 2k odd vertices. So here k is 3. It says that then there exist k edge disjoint subgraphs such that they together contain all edges of G, and that each is a unicursal graph. That means each of the k disjoint subgraphs will be an unicursal graph. Let me try to find. Okay, what it says, say, can you find 3 unicursal subgraphs or 3 edge disjoint subgraphs in which you will find some unicursal graph? So you need to find 3 subgraphs. What I'm saying, okay, so if you forget about the newly added vertices, then all the previous vertex, So that means your previous graph, and that was a universal graph. So you can see that this is an uh, subgraph of the whole graph. So if I consider the old one, the initial old one, and not considering all the new vertices, so this is our old subgraph, right? And in that subgraph, the this is the universal line or the Eulerian line. As a result, this subgraph is a universal graph. Now you have this one as your new subgraph, and these two subgraphs are edge disjoint. This subgraph and the previously formed subgraph, they are edge disjoint because there are no common edges in between. And another graph is this subgraph, and it has also edge disjoint. So it is also edge disjoint with the other graph. So there you can find, you have already found three subgraphs, right, which are edge disjoint, and which are, each of these subgraphs are universal graph, because here this is, so here you can see that f8 b and 9. So this is a universal line, and that gives to G. Okay, and here also in this subgraph you have, if you start with H, then 11 you go to E, then 10, and then I. Okay, so this is also a universal line in this subgraph, and this is a universal graph in this subgraph. As a result, each of these subgraphs are universal graphs, and each of these subgraphs are edge disjoint because there are no common edges between this subgraph and this subgraph, or this subgraph and this subgraph, and so on. So now I think the statement will be clear to you. Now, can anybody be able to tell me some idea about the proof, how this could be proved? Any guess? I'm just giving you some hints. Okay. So here, how many odd degree vertices are there? So there exist k odd degree vertices. Okay. Sorry, not k, 2k many odd degree vertices. That means you can pair them up. For example, I can pair these two together by drawing an edge, a newly built edge. So I am drawing a new edge here, okay, between these two odd vertices. Since they were initially odd degree vertices, after introduction of a new edge, now the degree of this vertex become 4. That means even. Similarly, by introducing the new edge, the degree of this vertex was initially 5, now it becomes 6. And initially it was 3, now it becomes 4. Okay, do the same thing. So here also I just put another edge here, and here also I put another edge here. So now you can see that the degree of each vertices is even, because it was initially, they were only the odd degree vertices. Now I paired them up. As a result, now the degree of each vertex is even. Just now I mentioned from the proof of Euler's theorem, it says that if the degree of each vertex is even, then that must be an Eulerian graph because it's a connected graph. That means it will certainly have an Eulerian line. That means a line or a closed work which starts from some vertex and end up with that vertex, and that should explore all the edges exactly once. So you can find such edge. Some, for example, say come try to explore all the things till say one vertex, and when you come here, then just explore all the remaining vertex and so on, and it will come back here, right? Since this is Eulerian, so up to B it was okay. Now up to B, if you just in the new graph, if you just put the extra edge, like say I if I put this extra edge like E1, and then say E2 and E3, Then from B you can just go to use E1 to go back to A. That means you start with A, come back to A. Now just 3, when you come to B here, when you come to B here, you just extra do one extra work. That means from B you go using 9 to go to G, and from G you use E2 to go to F, and from F you use 8 to go to back to G. So sorry, go back to B. So you start with B and comes back with B using this path, right? Sorry, I made, yes, E2 was used here. Similarly, when you are at D, when you are at D, you just use this, sorry, not at D, but at E. When you are at E, use that path. So that extra thing, and you will explore. As a result, what you will do, start from here, you will explore all the edges exactly once, and you come back here. Now in this case, for example, okay, I'll just write it down from here. So here A1, C2, D3, A4, B. Now when you come to B, that means when you come to B here, you just do extra work, like from B you use say 8 to go to F, from F you use E2 to go to G, from G you use 9 to go back to B. So B to B, this part is extra. Then again you are here, then use 5 E. When you are in E, you do the extra thing. You are in E now. So use 11 to H, then use E3 to I, then use 10 to E again. So this is again extra. And then you are again in E, then use the remaining part. It says you are in 6 D 7 B. Now when you are in B, you just use E1 to go back to E1 to go back to A. So you start with A, you come back with A, and you explore all the edges exactly once. So because it's an Eulerian graph, so you will certainly find some Eulerian line. Now what I am saying, what extra things that you have added? So you have added these extra edges. So here this extra edge, this extra edge, and this extra edge. So that were added into this graph. Now just remove this extra edges. That means if you remove this, then what will happen? It will be disconnected from here. You cannot go back. So up to this, you will have one. You will have one such. I can say one such trail, or you will have one such walk which is open. It starts from A, it ends up at where? It ends up at F. Where is F? It ends up at F. So like this. Now from E2 it starts from G, and it ends up at 5 to E. Where from E it comes from? I think it's something else. 5 to, I think it's 9, not E. Yeah. What is that? From 5? No, not 5. So B, from B I have gone to this by using 9, and it goes to G actually. Okay, I think you understand the way that I am trying to explain it. So just cut down from here and go till H. Okay, and from here, from I to this. Okay, not from I to here, E2, 3, and this. Yeah. not here. So you don't need to come back to A once again, right? So what you find, so this is one subgraph, this is one subgraph, and this is one subgraph. And here in this subgraph, you will find this is nothing but, and the that I mentioned, the definition which contains all the edges exactly once. And in this subgraph, all the edges are explored exactly once. In this subgraph, all the edges will be explored exactly once. Is the proof clear to all of you, or shall I repeat? Okay, I'll just read it from here. Then I think it would be more clearer to all of you. Okay, so that's the basic idea about this uh, statement. Let me explain. So in this universal graph, yes. So this is the, so in a connected graph G with exactly 2k odd vertices, there exist k edge disjoint subgraphs such that they together contain all edges of G and that each is a universal graph. Okay. So what it says, so let the odd degree vertices of the given graph be named as V1, V2, Vk. Another k are say W1, W2, Wt in an arbitrary order. Add k edges to G between the vertex pair V1, W1, V2, W2. Like for me, so I just paired them. This one and this one were paired. This one and this one were paired, and this one and this one were paired. And add the edges to join them. Since every vertex of G dash, so the new graph is now G dash. Since the every vertex of G dash is of even degree, G dash consists of Euler line row. Now, if we remove from row the k edges we just added, row will be split into k works, each of which is a unicursal line. See, if you remove this one, then what will happen? Okay, let me draw this once again. Let me draw this graph. It will be easier for you to understand. Okay. Okay. So let us have this theorem first. It says that in a connected graph with exactly 2k odd vertices. So I am preparing a new graph from here. Some new graph are being made from here. So I'll just some extra, put some extra. Okay, so up to E, say E, up to E, I think E is the last vertex name. Say F, G, H, and then I. So 7 was the last vertex. So I think it's 8. So the last edge, 8, 9, 10, and 11. So this is now my original graph. So suddenly this will not be a universal graph till anymore, because if you by chance if you come here, you won't be able to come back here, because then you have to explore 8 twice. Now let us try to explain this theorem statement. It says that in a connected graph, of course, this new graph is a connected graph with exactly 2k odd vertices. Let us try to find who are the vertices having odd degree. So this is the vertex of odd degree, no doubt about that. So this is the vertex of odd degree. Okay, Okay, so this is the vertex of odd degree, this is the vertex of odd degree, this is the vertex of odd degree. 1, 2, 3, 4, 5. This is the vertex of odd degree. So even this is the vertex of odd degree, this is the vertex of odd degree. So how many? 1, 2, odd degree vertices. That means this is 2 into 3. That means 2 into k. So here k equal to 3. Okay. So it says that in a connected graph with exactly 2k odd vertices. So here our k is 3. Then it says that there exist k edge disjoint subgraphs. So in this graph, it says that there must exist k edge disjoint subgraphs. Okay, such that they together contain all edges of G. So you need to find three edge disjoint subgraphs here. That subgraph should contain all the edges of G, that means all the 11 edges of G, and each of the subgraph is a unicursal graph. That means in each of these subgraphs we'll be able to find a unicursal line. Okay, so first try to what is the graph the odd degree vertices. For example, here I am just pairing this 6 odd degree vertices as 3 pairs. For example, I am pairing this vertex with this vertex. Both of them are odd degree vertices and I join them and I call this new edge as E1. Okay, now I pair this odd degree vertices, I call this as E2. I pair these two odd degree vertices and I call this E3. So I have added E1, E2 and E3. Now you can see that each of the odd degree vertices, now the degree has been even. So here the initially the degree was 3, now the degree is 4. 2, 3 and 4. Similarly, initially the degree of this vertex was 4, now till it's no modification 1, 2, 3, 4, 5. Okay, let me check 1, 2, 3, 1, 2, 3. Okay, what is the degree of this? 1, 2, 3, 4, 5, and 6. So now the degree of this vertex becomes 6. Okay, now the degree of this vertex becomes 2, and so on. So, and by making them a pair, you can see that each of these vertices are now of even degree. So just now I mentioned you this result that each of this vertex, since this is of even degree, it must be an Eulerian graph. So it must contain an Eulerian line. That means you must have some of the line or trail which starts from here and which end up at here, exhausting all the edges exactly once. Now somebody please tell me what could be this trail. Okay, it starts with A, say it goes to 1, then it goes to C, then it goes to D. Okay, colpo, can you please repeat once again the trail that you mentioned earlier? Or can you please repeat to have the Eulerian path, Eulerian circuit?
Sir, I mentioned from A to C via 1,
Okay, just a minute. Okay, just a minute. A to C by 1, yes.
then C to D by 2,
To D, yes.
then D to A by 3,
So 3A,
then A to B by 4,
4,
then B to D by 5,
5,
then D to E by 6,
and then
then by 7
7B. So that was the trail explained by Kolpok for this initial graph, right? So for this part only, for this part only for this part. Now I extended this graph till this. Okay. So what I'm doing, whenever you come here, whenever you are here at some point, for example, B. So you come here, B. I'll just add extra. I just explore through this. What is there? I will do like, so from B, I will use 9 to go to G, and from there I'll use E2 to go back to, I think it's F, right? It's F. I will. So now you can see that when I come B to B, I will just explore this path to again come back to B. Now when I am in C, so I am in C, 6, and so this is E. So I am in E. When I will come back to E, I will just explore this path. So from E, I will use 10 to go back to H. Then I will use E3 to go back to I. And then from I will use 11 to go back to E. Okay. So you can see that I will come here. So now the whole path looks like this. A1, C2, D3, A4, B, then 9, G, E2, F, 8, B, and then again 5, D, 6, E, then 10, H, E3, I, 11, E, and then 7, B. Now you can see that this is out of which 4B, B, then 9 up to B is your new addition, and from here after E you have this, your new addition, right? Now if you are going to drop this, the new extra edges for here, the new extra edges were E2, E1, and E3. Now try to like this and just drop this edge up to, where is E1, up to this, from here. So I think it is E6, 6, 6 to E. No, this is not E1, sorry. So this is just E. So I think it should be not from here. Yes, it should be from up to this, and then from here to 7. And from B, so B2, from B2 you can come back to A by E1. So actually it should be from B using E1, you should come back to E. So it starts from A, it come back to A by using some Eulerian line. Now you just come to up to B. So you see that I have taken three part of it. First one is this one, second one is this one, and third one is this one. So I say that they are basically, so just can you just see how they look like? For example, A21, so maybe I'll just reduce it. So here from A to 1 to C to 2, then A, then 4, then B, B2, then use 9 and go to G. So this one is a subgraph. then F to 8, 8 to B, and this is another subgraph, and this is another subgraph. So now you can see that three edge disjoint subgraphs are there, and each of them will contain a kind of unicursal line. So all of them are unicursal line. And if you join all of them, you will certainly get all the edges of the original G exactly once. So that is the proof of this theorem. Is the proof clear to all of you now? Is the proof clear? Any question or comments? Any question or comments? Okay, so I hope that you understood this proof. And if you understand this proof, then few operations that you need to understand, it's very easy. If you read this from this book, that will be clear how to join two graphs, how to add two graphs, how to delete, what do you mean by deletion of a one vertex, and decomposition and all. So I will just give this operations for you as an homework. Just have a look at this graphs, and that will be very easy to understand. And from then, in the next class, I will basically talk about Hamiltonian path and circuits.